All right, hey guys, back for the last couple of days of this chapter, both on L'Hopital's rule. I don't know why I have two here. There should be a one there. This will be L'Hopital's rule, part one. The indeterminate forms that we're going to see today are 0 over 0, infinity over infinity, infinity minus infinity, and 0 times infinity. So L'Hopital's rule is specifically applied to evaluating limits. And these are the four indeterminate forms that we're going to talk about today. So let's go ahead and get started. So L'Hopital's rule, if the limit as x approaches a of f of x over g of x either comes out to equal 0 over 0 or plus or minus infinity over infinity, we cannot say that the limit doesn't exist. We've got more work to do. So what we do is, provided that the derivative exists or both functions are differentiable, then we can take the derivative of both the top and the bottom and reevaluate. Now, one key thing to doing that is we must simplify first. I'll explain in the examples that follow. Okay, so let's take a look at our first example. All right, so the limit as x approaches 0 of sine x over x. Now, we don't ever technically want to write 0 over 0. So what I'm going to do is I'm going to evaluate the limit of the top. And as x goes to 0, sine x goes to 0. And the limit of the bottom. Since I would have the form 0 over 0, or that indeterminate form, then by L'Hopital's rule, the limit as x approaches 0 of sine x over x is then equivalent to the limit as x approaches 0 of the derivative of sine x, which is cosine x, over the derivative of x, which is 1. Okay, now a lot of students will misinterpret this and use the quotient rule. That's not what we're working with here. And we can see that the limit as x approaches 0 of cosine of x over 1 equals 1. All right, so that just confirms our special limit that we've talked about before. All of this work right here is necessary in order to get full credit. Okay, let's look at example number 2. Limit as x approaches 0 of 1 minus cosine x over x. Okay, we'll do this in a different color. So the limit as x approaches 0 of 1 minus cosine x would equal 1 minus 1, which is 0. And the limit as x approaches 0 of x also equals 0. Therefore, by L'Hopital's rule, the limit as x approaches 0 of 1 minus cosine x over x is equal to the limit as x approaches 0 of the derivative of both of those. The derivative of 1 minus cosine x is a positive sine x. The derivative of x is 1. Therefore, the limit as x approaches 0 of sine x equals 0. That was another special limit that we've worked with. Again, follow suit with all the correct notation and all of that good stuff. Okay, let's look at a more complicated example here. So now, why do I have as x approaches 0 from the right? Well, that's because the natural log does not exist to the left of 0 or at 0. All right, so it's just a technicality with that function. Okay, so let's take the limit as x approaches 0 from the right of negative ln of x. If you were to visualize that, here's what negative ln of x would look like, where this would be the point 1, 0. Okay, so clearly as x approaches 0 from the right, that's going to a positive infinity. Likewise with the denominator, the limit as x goes to 0 from the right of cosecant of x. Well, cosecant is the reciprocal of sine. So here's sine at 0. Cosecant at 0 would also be approaching 0, or excuse me, infinity. So therefore I'd have the form infinity over infinity, which means that by L'Hopital's rule, then the limit as x approaches 0 from the right of negative ln of x over cosecant of x would equal the limit as x approaches 0 from the right, derivative of negative ln of x would equal negative 1 over x over the derivative of cosecant. Well, the derivative of secant is secant tangent, so the derivative of cosecant is negative cosecant cotangent. All right, so we've got a little bit of work to do here because this is kind of messy. And what I said earlier was you need to simplify. So if I were to simplify, let's do a little work with this. Let's use some trig. So this would be, let's just negate the negative values. So this would be 1 over x over 1 over sine x, and cotangent would be cosine x over sine x. See if we can manipulate this. Okay, so 1 over x is going to then, how can I manipulate that? Let's see. I would have, let's go with limit as x approaches 0 from the right of, I'm going to take the reciprocal of the denominators, bring them to the numerator. Reciprocal of the numerator, bring it to the denominator. Okay, so that would be sine x on top for this term. 1 over x becomes x on the bottom. And then I would have another sine x over cosine x. Right, so I took the reciprocal of this function, just flipping, putting the sine up here and the cosine down here. Okay, so let's think about this logically. So the limit as x approaches 0 from the right of sine x over x times, I can use the property of limits here, limit as x approaches 0 from the right of tangent x. Well, I know that this limit, this first limit here, evaluates to 1. What would this evaluate to? Well, as I look at the graph of tangent, right, where these are asymptotes at x equals negative pi over 2 and pi over 2, then it looks like as we approach 0 from the right, tangent is approaching 0. So it's a simple substitution. Therefore, this actual value, infinity over infinity, ends up equaling 0. So the limit as x approaches 0 from the right of negative ln of x over cosecant of x ends up equaling 0. Let's do one more example on the next page. Okay, so number 4, this is a weird example. If I were to plug in 0 from the right, I would get a 0 limit as x approaches 0 from the right of x. Well, that'll equal 0. And the limit as x approaches 0 from the right of ln of x would equal negative infinity. So really my indeterminate form here is 0 times negative infinity. All right, so I can't use L'Hopital's rule yet. What I have to do is get this into a form where it either is equivalent to 0 over 0 or negative infinity over infinity. And here's how I can do that. When you get this 0 times infinity form, what you want to do is you want to somehow get it in a form like this, right? Some kind of division, some kind of ratio or quotient. Okay, so now if I look at this in a different light, if I look at 1 over x coming from the right, that's going to equal 1 what would that equal? That would equal 1 over 0, which would be infinity. And of course, I already looked at the other limit as x approaches 0 from the right of ln of x equals negative infinity. So I'd have a negative infinity over infinity, which is now in a L'Hopital's form. So therefore, by L'Hopital's rule, then the limit as x approaches 0 from the right of ln of x over 1 over x will be equal to the limit as x approaches 0 from the right of 1 over x, which is the derivative of ln of x, over negative 1 over x squared, which is the derivative of 1 over x. Now let's do a little bit of simplifying. This would be equal to the limit as x approaches 0 from the right of negative x. Now, how did I get that? I took 1 over x, multiplied it by negative x squared. Right? The reciprocal, instead of dividing by negative 1 over x squared, I multiplied by negative x squared. So, of course, this would evaluate to 0, and therefore 0 times infinity in this case ends up equaling 0. That's not always true of those forms. This form could actually equal 1. It could equal something else. It depends on the functions. Okay, let's look at an example where we have to use L'Hopital's rule more than once. Okay, the limit as x approaches 0 from the right. Again, ln has that restriction, so we got to use it, of ln a cosine of 5x. Well, that's going to equal the cosine of 0, which is 1, and ln of 1, which is equal to 0. Okay, same thing is going to happen here. Limit as x approaches 0 from the right of ln of cosine of 3x. Well, that'll still equal ln of 1, which is equal to 0. Therefore, by L'Hopital's rule, the limit as x approaches 0 from the right of the ln of cosine of 5x over the ln of cosine of 3x, it's going to get kind of messy here. We're going to take those derivatives, will be equal to 1 over cosine of 5x times the derivative of cosine of 5x. So that's going to equal negative sine of 5x over cosine of 5x. Likewise, in the denominator, we'll get negative sine of 3x over cosine of 3x. Now I could write that as the limit as x approaches 0 from the right of, negate the two negatives, which would be tangent of 5x over tangent of 3x. Okay, now I'm kind of working right to left here, so I hope you're okay with that. But the limit as x approaches 0 from the right of the tangent of 5x equals 0. And the limit as x approaches 0 from the right of tangent of 3x also equals 0. Okay, so we have a problem. So we did L'Hopital's rule, we simplified, we evaluated, we still got 0 over 0. Potentially, actually it will end up working out. You might have to do it 2 or 3 times, but we're going to use L'Hopital's rule again. The limit as x approaches 0 from the right of tangent of, that should be a 5x over tangent of 3x will equal the limit as x approaches 0 from the right. The derivative of tangent is secant squared. Okay, so this will be, and then the derivative of 5x is 5. So 5 secant squared x over 3 secant squared x. Excuse me, that should be secant squared 5x and secant squared 3x. Okay, now the limit as x approaches 0 from the right of 5 secant squared 5x over 3 secant squared 3x. I just know it's coming here, but the secant of 0 is 1. And therefore, secant squared of 0 is still 1. Therefore, we would get a limit of 5/3. Okay, now, I did something wrong here. Or no, did I? Yes, I did. And here's what I did wrong, okay? So I should have had a 5 here and a 3 here, which would have made this 5 and 3, which would have made this 25, oops, which would have made this 25 and 9. So I should get a 25/9 here. My bad, I forgot my derivative chain rule action along the way. Okay, so the limit as x approaches 0 from the right of ln of cosine of 5x over ln of cosine of 3x ends up equaling 25/9, even though we got the form 0 over 0. All right, let's keep working. Okay, 2 more examples here. These are examples of infinity minus infinity. Okay, so let's take a look at why they are that form and how we work with it. So if I took the limit as x approached 0 from the right of 1 over x, I would get positive infinity. And if I took the limit as x approaches 0 from the right of 1 over sine x, I get 1 over 0, which of course is infinity. Now we can't use L'Hopital's rule until we get this in a form of 0 over 0 or infinity over infinity. So the method you want to use in a situation like this is you want to get a common denominator. So you would get sine x minus x over x sine x. There's my common denominator. Now we work and we see what form we get. And typically it'll end up being a form that we want to use L'Hopital's rule. All right, so the limit as x approaches 0 from the right of sine x minus x ends up equaling 0. And the limit as x approaches 0 from the right of x times sine x also equals 0. Therefore, by L'Hopital's rule, then the limit as x approaches 0 from the right of sine x minus x over x sine x will equal the limit of the derivatives of the numerator and denominator, which will be cosine of x minus 1 over, we got to do a little bit of product rule here. Derivative of x is 1. Derivative of sine x is cosine x. Now we're going to evaluate, okay? So I'm going to use this limit as x approaches 0 from the right, cosine of x minus 1 over sine of x plus x cosine of x. We might have to do L'Hopital's rule a second time here. I'm not sure yet. And if we do, I'm going to be in trouble because I'm gonna have some issues. So limit as x approaches 0 from the right of cosine of x minus 1. Well, that's going to equal 0. Limit as x approaches 0 from the right of sine x plus x cosine x. Well, that's going to equal 0 as well, right? I'd get 0 and 0 times 1, which is 0. So by L'Hopital's rule, now I'm not going to follow my same format, but you would need to. By L'Hopital's rule, this would be equal to the limit as x approaches 0 from the right of negative sine x over, derivative of the bottom would be cosine x plus cosine x minus, that would be derivative of x is 1 minus sine x. Okay, I see what we're going to get here. The limit of the top, if I were to evaluate, plug in a 0, I would get 0. Limit of the bottom, if I plugged in 0, I'd get 2 minus 0, which is 2. Therefore, this limit, infinity minus infinity, comes out to equal 0. All right, you guys, that was a messy one, but again, you got to use that form, get a common denominator. Let's look at one last example. That'll be it for part 1 of L'Hopital's rule. Okay, let's do this last example here. Limit as x approaches pi over 2 from the left of secant squared x minus tangent x. Let's look at both of those functions and determine what's going on there. So I know that tangent has a vertical asymptote at pi over 2. And the function approaches infinity as it approaches pi over 2 from the left. Therefore, the limit as x approaches pi over 2 from the left of tangent x equals a positive infinity. Okay, let's look at secant squared. Well, secant squared is closely related to cosine. Cosine has a 0 or an x-intercept at pi over 2. Therefore, secant would have a vertical asymptote there. Thus, secant would approach infinity. Therefore, secant squared would also approach infinity as x approaches pi over 2 from the left. All right. Now, what I would do is, this is an indeterminate form. It's the indeterminate form infinity minus infinity. I'm going to see if I need to use L'Hopital's rule. If I do, great. I'll use it. I'll evaluate. I'll then simplify and evaluate again if necessary. So let's see what form this takes on. So the limit as x approaches pi over 2 from the left of secant squared, well, secant squared is 1 over cosine squared. Tangent is sine x over cosine x. So just like we did in the last example, I'm going to combine these, getting a common denominator, and see if I need to use L'Hopital's rule. It's potentially true that I do, or possibly that I don't need to. If I get a common denominator, I get 1 minus sine x cosine x over cosine squared x. Now if I evaluate that and I plug in a pi over 2, sine of pi over 2 is 1, cosine of pi over 2 is 0. So I get 1 minus 0. Cosine squared, well, what is the cosine of pi over 2? Cosine of pi over 2 is 0, so I get 0 squared. If you ever get an answer where you get a number over 0, you are done. This limit does not exist. So in this case, I didn't need to even use L'Hopital's rule, but only if I do have to transform it into a form that could potentially give me L'Hopital's rule, which in this case is common denominator. Okay, guys, that's it for L'Hopital's rule part 1. We'll be back in the next video with part 2. Have a great day.